Hi everyone, let's look at high resolution H NMR. Before you watch this video, make sure you have already learned about low resolution H NMR. So just to recap a bit, in a low resolution H NMR, the number of peaks indicate the number of different environments which hydrogens are found, and the integration trace or the intensity of the peak indicate how many hydrogen are there in this particular environment, and we use chemical shift values to indicate what type of proton we're dealing with. Now, in high resolution H NMR, we're going to have more information in terms of splitting patterns. So what happens is that when a hydrogen attached to a particular carbon interacts with the spinning of a hydrogen which is attached to an adjacent carbon, there's going to be different combinations of magnetic fields that are going to be produced. So this results in a splitting pattern. So let's take, for example, this ethanol molecule here. So these three hydrogen, they are in the same environment. So they are attached to a CH2OH. So they are in environment. Now, when you look at the adjacent carbon, so this is the adjacent carbon, this one is attached to two hydrogen. So there's two hydrogen on the adjacent carbon. Now, these two hydrogen, they're also going to spin, and their spinning is going to affect the signal produced by these CH3 protons. Let's try to look at these protons now, these two. So here you have one adjacent carbon and another adjacent carbon. So in total, this one has 3 hydrogen and this one has no hydrogen. So in all, this one has 3 hydrogens that are attached to the adjacent carbon. If we look at these protons now, they don't even have an adjacent carbon. So there is no hydrogen on the adjacent carbon. Now let's take this methyl group, for example. So this methyl group has an adjacent carbon which is bonded to one proton. When you apply an external magnetic field, what happens is that this adjacent hydrogen can either spin in the direction of the external magnetic field or against the external magnetic field. Both situations that have equal chances. Now, this effect is going to couple with the spinning of the CH3. It's going to produce a spin-spin coupling, and the spin-spin coupling is going to cause the signal due to the CH3 protons to split into 2 equal peaks of the ratio 1:1, and we call this a doublet, which means that when you look at a low resolution NMR for that CH3, let's say, so we would see a single peak with intensity 3. So intensity 3, integration 3. But when we look at a high intensity NMR, we would see that same peak at the same chemical shift value that has split in a doublet, ratio 1:1, still integration 3, so the intensity will still be 3, indicating there's 3 hydrogen, but you'll see that there is a doublet. So the doublet gives us additional information, meaning that these 3 protons have an adjacent carbon with 1 proton attached to it because it has a doublet. Now, if those 2 adjacent protons, what will happen is that these 2 adjacent protons can spin in the direction of the external field. One can be in the direction of the external field and one other is going to be against. And you can also have both of them being against the external magnetic field. So this gives us 4 different combinations, but if you look at these two, these are the same. So you can have chances in the ratio 1:2:1. So this is going to cause the peak due to the CH3 in this case to split into a triplet due to the 2 hydrogen on the adjacent carbon. If there's 3 adjacent hydrogens, then you're going to have 4 peaks in the ratio of 1:3:1. It's called a quartet. So we can summarize the information. If you have 1 hydrogen on the adjacent carbon, you get 2 peaks, which is called a doublet. If you have 2 hydrogen on the adjacent carbon, you get 3 peaks. If you have 3 hydrogen on the adjacent carbon, you get 4 peaks. We can also have information about the splitting patterns. So singlet means there is only 1 peak, and here you have no hydrogen on the adjacent carbon. Doublet, 1 hydrogen. Triplet, 2 hydrogen on the adjacent carbon. Quartet, 3 hydrogen on the adjacent carbon. You can also have what we call a multiplet if you have more than 4 hydrogen on the adjacent carbons. Now you can easily recall the intensities of the peaks by using the Pascal's triangle. So the first line, so when you have singlet, so ratio is just 1. If you have a doublet, ratio is 1:1. If you have a triplet, you can just combine 1 plus 1 is 2. That would be for triplet. For quartet, you can just add these two. 1 plus 2, 3. 1 plus 2, 3, and so on. So you can use the Pascal triangle to recall the ratio of the peaks. No need to learn them by heart. Now, the TMS, tetramethylsilane, is used as a reference point in low resolution NMR or high resolution H&MR as well, and it's used because of the following reasons. You have to know these reasons. You have 12 protons that are in the same chemical environment, therefore it gives you a single strong peak. It's non-toxic, therefore it can be used safely. It is also unreactive, therefore it's not going to react with the samples that we're testing. It has a low boiling point, which means that once we are done testing, we can remove it easily by just heating it. And it also has lower electronegativity actually than carbon. Therefore, the peaks are going to be upfield. When you look at an NMR spectrum, when the chemical shift value is close to 0 in this direction, we call this upfield. And as chemical shift values go lower, it's called downfield. So because of the lower electronegativity of silicon, it causes the chemical shift value to be very upfield, which means that all the chemical shifts for organic compounds are going to be downfield in comparison to TMS. Hence, there is no interference between the